Hello, this is semester one review for pre-calc honors. I am just in this video doing the unit one review. The problems I'm going to do, not that the other ones aren't relevant, but these are ones I think are the most important to look at, are 1, 4, 5, 14, and 15. So first starting out with 1, it's very important to be able to go back and forth between linear combination form and component form. So if you have here hold on a second, I'm going to have to pause and restart. Okay, now I'm good. My smartboard was not plugged in properly, so now I can write. Okay, so you have linear combination form for these three right here. You also should be able to go back between component and linear combination form. So component form of A would be 1, 1, -2, as you have coefficients of I, J, and K. And then also you should be able to write it in column vector form, be 1, 1, -2. Same with B and C. Okay, A is saying we are going to take 2 times A, which is I plus J minus K, plus 3 times B, which is 3I minus 2J plus K. You're going to do this in linear combination form. So the 2I plus 2J minus 2K distributed into all plus 9I minus 6J plus 3K. And then your just adding variables. So 2I and negative, 2I and 9I, which gives you 11I, cross them out. 2J minus 6J is negative 4J. And then negative 2K plus 3K is plus K. You could also have done a linear combination or component form, and you're just adding the like terms. Okay? Okay, moving on to B. B's notation means magnitude. Double bars like that mean magnitude. If it's single bars and it's a vector, that doesn't mean absolute value means magnitude. In fact, magnitude is the absolute value. It's the distance it has traveled from its original position. So the magnitude is root sum of the squares based on Pythagorean theorem. So B is 3 squared plus negative 2 squared. I don't have to write the negative because we're squaring it. Plus 1 squared. So 3 squared is 9 plus 4 is 2 squared is 9 plus 4 is 13 plus 1 is 14. So root 14, that's the magnitude of B. C, that notation means the dot product. We're taking the dot product between A and B. So A dot B, I'm going to do this one in component form because I prefer that particular dot product multiplied, dotted with B is 3, -2, 1. And the dot product is taking the like parts, multiplying them, and adding them all together. So like components, 3 times 1 plus the B values, or the Y components, so that'd be 1 times -2 plus the Z components, -2 times 1, so -2 times 1, and this is definition of dot product, that equals 3 minus 2 minus 2, which gives you the dot product between A and B. A dot B equals -1. And note, dot product is a scalar. Very important to understand that's a scalar, which we'll get into in further problems. D, the cross product, not the dot product, but the cross product of A and B. So the cross product is we do a matrix. We're taking the determinant of the matrix. That's what FR means when we get the second semester. That will become more clear. So the first row is IJK, as I have there. The second row is the first vector A, and then the third row is the second vector B. Okay, so it's very important that you do it in order. If you flip them, you'll get the opposite vector. So that would be B cross A rather than A cross B if you interchange row 2 and 3. Okay, so first we have I multiplied by the determinant, which will of 2 by 2 matrix in there, which we'll figure out, minus J multiplied by something plus K multiplied by something. Hopefully I put my numbers in there. Okay, how do we find I? We look at where I is, and we delete the row and column of I, and we're left with right here that matrix right there. So what we do is take the determinant of. The determinant of is that times that. 1 times 1 is 1. Minus, we always do minus, so this is A, B, C, D. We do A times D, that's A times D, minus B times C, which is -2 times -2. That times that. Negative 2 times negative 2 is 4. Okay? That's how we do cross product. Give me a second, I'm going to do a little erasing here. Now we're going to do the same thing for J. Note I had erased all that and erased also the work in front of I, so I just replaced it with what it is. It's 3. 1 times 1 minus 4 should be negative 3, not positive 3. Sorry, it should have been negative 3. Is checking it. 1 times 1 minus 4 is negative 3. Yes, okay. So now we want to do the same thing for J. So we take J, we cross out the columns in the row that J's in, and now we have this, and we do the determinant of that 2 by 2. So that's 1 times 1, which is 1, minus negative 2 times 3, which is negative 6. So that would turn to, that minus the negative turns positive. That will end up being 7. And then we do the same. I'm not going to erase in the interest of time for myself more than you, since I can pause it, but you get that. Yeah, okay, so we can hopefully see this. So disregard the green there. If I cross out the K's, we have that, so that'd be 1 times negative 2 is negative 2, minus 1 times 3, which is 3. So minus 3. Now we simplify all that, and we get negative 3i minus 7j, when 6 plus 1, you got the negative out front, minus 5k. Hopefully I didn't make any mistakes. Right there is the cross product. And what is the cross product? If I have a vector A going in that direction and B going in that direction, we found the cross product, which is a vector that is orthogonal, which means perpendicular to both A and B. That's what the cross product does for us. It can become very physically relevant as we get to move forward in mathematics. Okay, E. E is saying, I'm not going to go through E, but E is saying you take the cross product of B and C, and you do the same process we did in D, and then you take its magnitude. So you're doing on the vectors B and C, you're doing the process for D, and then you are doing step B, well, we did in B, the magnitude. You're doing that for your B cross C vector. Remember, this vector is going to be a vector just like that is. You do the magnitude of it, okay? So the work or the answer's on there. Go ahead and try it yourself. F. A dot B cross C. Okay. Okay, not going to work out all of this, but what we do first, just like you did in E, you're going to find B cross C, and then you're going to get some vector. You're going to get some vector right here. And then this is saying now you are going to take A and dot it with that vector. So whatever that vector is, A, which is 1, 1, negative 2, I believe. Yep. And then whatever this vector is, you are simply going to dot it, just like you did the dot product in C. Okay, so we got F, that's number 1 for you. Moving on to number 4, find the equation of parametric, find parametric equations for the lines. Okay, so the form of parametric equation, you can go and skip all of this if you are solid with the equation, but a little review would be good. I'm going to go through why this is your parametric equation. So if I have a line 3 dimensions, I have a line 3 dimensions here, okay? If I have a vector v like this, v, and this line, let's call it Q, line Q, okay, is, no, I'm not going to call it Q. I'm not going to call it anything. I'm going to call this point P and this point Q, which is on the line. Let's say V and the line PQ are parallel to each other, meaning they're going the same direction. Okay, so we have our initial point, which is x1, y1, z1, and the second point is going to be generalized as x, y, and z. Because we're only, for the parametric equation, we only need one variable specific point, x1, y1, z1. X, y, z is our generalized x, y, and z, as you see on the left. So see here, we have x, y, z, we have x1, y1, z1, and we have a, b, c. The only thing within this equation is we don't have t. Well, two vectors are parallel. PQ, if PQ is parallel to V, then PQ is going to be some scalar of V, or V is going to be some scalar PQ. Okay, so we do it, so we take v and we multiply it by t, and now the vector tv is t distributed in, gives us, I'm going to write the a and the b and the c first. At, bt, ct. Now that's a scalar. T is like 2 or 3 or whatever you multiply by each component. Okay, the vector pq, and note, it is important why I'm going through this because it helps us, it really breaks down the mathematics of why these variables are what they are. It makes the questioning much easier if you understand why those variables are what they are. PQ, that's a vector based on the terminal and initial. So the terminal is x, y, z. The initial is x1, y1, z1. So the vector PQ is x minus x1, any minus initial, y minus y1, and z minus z1. Okay? So those are our two vectors. They're parallel to each other, and they're parallel to each other. Well, we have right here that they are equal. If PQ is parallel to V, is equal to it, provided that it's multiplied by some scalar. So now we can set each part equal. We can set that equal to that equal to that, and this equal to that. So now that I've made it all messy, let's go ahead and do that. X minus x1 equals AT. In blue here, I have y minus y1 equals BT. And lastly, in red, I have z minus z1 equals CT. Now, if we move those constants over, we end up getting those equations right there. So the reason I went through that is, one, you see why it is what it is. And then we know that x1, y1, z1 is some point, some random point on the line, and A, B, C is the directional numbers for the vector that is parallel to PQ. So a vector PQ, that's the direction in which P is facing. Okay, so let's look at for A. It gives us, and I'm going to, hold on. Okay, so now for 4A, it gives us, we have at least 1 point, so we can call that x1, y1, z1, or you could have called 1, 1, 5 that as well. We have the point, but now we need the directional vector. Well, we have 2 points on, so we just do any minus initial to get our directional vector. So I'm going to write it like this: ABC, our directional vector, is simply going to be our ending minus initial. I'm considering 1 to be my ending, 1, 1, 5 to be my ending. So I have 1 minus 4, 1 minus negative 1, and 5 minus 2. So therefore, the directional is negative 3, 2, 3 is the directional vector. That's ABC. So now we just plug it in the formula. X equals x1 is 4, minus a, which is 3 times t, t is some scalar. Y equals negative 1 plus our b value from the vector, which is 2. And then lastly, we have z, which is the z value of 2 plus 3 times t. Now, if you use the other point, that's fine. And if you flip them around as well, then you just have the opposite vectors, which is fine, because then it would just take different t values to get to any point. So if I said find another point on the line, you just plug a value in for t. Let's say if we plug in, and this is all you're going to have to do for a problem like this. But what does this mean now? How do we find other points now? Well, we pick a value for t. If t equals 1, then that coordinate, that would give the coordinate where x equals 1, y would equal 1, and z equals 5. If t equals 2, etc., we get a bunch of points. Okay, so that's why that equation works for lines in 3 dimensions. Parametric equation. Okay. B, through that and perpendicular to the plane. So let's look at this graphically. If I have a plane right here, and I'm going to orient it nice for myself. We know we have a normal vector that comes out of plane. It's very important to understand the equation of a plane, which looks like this. And actually, we'll fit it all in. C, blah, 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 blah. That is the A, B, and C are the directional vectors of the normal vector of the plane, if you recall. The normal vector is any vertical or any vector that is perpendicular to the plane. It can be parallel transported anywhere. Okay, I mean to make those different lengths, okay? So a vector that's orthogonal to the plane, the components of those vectors are simply the coefficients there. So if I look up here, 2, negative 1, 5, that is the normal vector of the line, 2, negative 1, 5. The normal vector is perpendicular or orthogonal to the plane. So if we're looking for a line that goes through that point, well, there's our x1, y1, z1, and is perpendicular to the plane. That means if this is our plane, this line we're looking for is perpendicular to it, which means it has the same components of the vector in its direction as the normal vector. So they're giving you the answer. 2, negative 1, 5 is your A, B, C, and this is your x1, y1, z1, and then you go ahead and write it out. So that's 4. Moving on to 5, write the equation of a plane parallel to that through that point. Well, again, the equation of the plane, I'll write it out explicitly now. Actually, let's go through why it is. Okay, so if I have a plane here, I have a point which I'm calling, what do we call it? Q. We're calling this point Q, which is going to be x1, y1, z1. Actually, it doesn't matter. And here's a point P out here, point P, and P is x, y, z, generally. We then have a vector right here, which we're going to call the normal vector, and it's going to have components A, B, C. Now, we see that we have a vector PQ and the vector N are orthogonal to each other, so their dot product is 0. Okay. And therefore, if we dot the two of them, first off, PQ is going to be x minus x1, y minus 1, z minus z1, and e minus initial. And then N is, I'm just rewriting for clarity, A, B, C. That is the normal vector. If we dot that, that would be the components multiplied by each other, plus the components multiplied by each other, plus the components multiplied by each other. And since this dot product, since they're orthogonal, the dot product equals 0. And their standard form of a line, where ABC is its normal vector and x1, y1, z1 is some point on the plane. Again, going through that is important because now it's quite simple to see what, where we plug in what. Okay, so 2, 1, 0, that's x1, y1, z1. And if it's parallel to that plane, let's go and look at that. If I have two planes that are parallel, sorry, it's not the best drawing. Well, what would be true about their normal vectors? They'd be going in the same direction. Excuse me. So, the normal vector of this plane is 1, 4, negative 3. That's going to be the same normal vector of this plane. So, we plug in, what was it again? It was 1, 4, negative 3. 1 for A, 4 for B, and negative 3 for C. And then we have x, which the x coordinate of the plane is 2, so we have x minus 2, plus y minus, the y value is 1, and then we have minus 3, z minus 0, and that equals 0. Now, why does it look like that rather than this up here? Well, there they just distributed in the A, B, and C and combined all the constants. So it depends on what form. This standard form, this form up here is called general form, but typically you subtract the 1 over. But in any case, that's how you do it. Okay, so if we have 3 points, how do we get the plane? Well, if I have 3 points in space, I can draw 2 vectors through them. And then, and those are on the plane. So all those vectors are on the plane. If I take the cross product, I find a vector that's orthogonal to it. And therefore, if I have vector A and vector B, A cross B is going to be your normal vector. And then you use any of those points as your x1, y1, z1. Okay, I'm not going to go through the work on that. The other thing, let's say this is multiple choice, and I say, which plane is that on? Well, you could just plug it in the equation. So if I take 3, negative 1, 1, and plug it into this equation over here, it'd be 3 plus negative 4, which is negative 1, minus 3 is 1. I believe that point works. So that point satisfies that plane. I'd have to check the other two as well. You could do that, or you go through this. You get 3 points, you get the vectors between two of them, and then do their cross product. It really doesn't matter to work because you can do the cross product and be here, even if we're in the opposite direction, doesn't matter, it's still normal to the plane. Okay, so give that a try. So step 1, you find vectors A and B. You from the points, the 3 points, so vectors A and B, as I have documented up there. You start from one of those 3 points, you use as your initial, and do that. Well, then it really doesn't matter which one. If you use different initial for both vectors. In any case, you get A and B, then you do A cross B, and then this right here is going to be your ABC vector, and one of the coordinates that was given is going to be your x1, y1, z1. Okay. That's number 5. Let's move on to 14. Given these vector finding quantity, state whether it's a quantity is a vector, scalar, or not possible. So I'm not going to do the computations. We've already done most or all of these computations. We've done all of these. Dot products, scalars, addition of vectors, magnitudes. I don't know if it's a cross products, all in there. So what I want to focus in here is the stating whether it is going to be a vector, scalar, or not possible. So it's very important that the dot product, not prod, dot product is a scalar. If I take the dot product, it's going to return out a number. If I do a vector addition or subtraction, that's add or subtract 2 vectors, that's going to give us out a vector. And cross product is going to give us out a vector. Magnitude is a scalar. And if I scale up a vector, I multiply it by some number, we still get a vector. So it's important to know what your outcomes are for each of these. Okay, so let's look at A first. A, if I take the dot product, that will give us a number, and I have 2 times a vector. How do I know that U, W are vectors? Well, they tell us above. So first off, I'll just write out like this, 2W. The first part is a dot product inside the parentheses, and then 2 times W is a vector. So if I have the dot product, which is a scalar times a vector, we are going to get out a vector. Okay, B, I'll just talk through this. That's a scalar times 4, that's a scalar, so I'm going to put S. Plus, right here is a scalar, so if I take a scalar, which is a number times a number, we get a scalar. So B is a scalar. C, if I take the magnitude of V, that's a scalar. Can I take a scalar and cross product with U? That is not possible because you can only cross product vectors, not a scalar and a vector. So C is not possible. D, the cross product, that is a vector. So if I have a vector, V stands for vector, dotted with a vector, that's going to give us a scalar. So D is a scalar. Okay, for E, I have a cross product multiplied by 3. So magnitude of the cross product. First off, inside here, W across U, that's a vector. And if I take the magnitude of a vector, you get a scalar, right? That's the length of it. So that times 3, a scalar times 3 is still a scalar. For F, this right here, as we just did in E, is going to be a scalar, and you can't dot a scalar with a vector, only a vector with a vector, so that one is not possible. Okay, so find a point that intersects with a line on a plane. So let's go ahead and look here. Let's say we have a line here that intersects with a plane. We see that a plane, provided that it intersects with a line, will intersect at a point, so we have to figure out what that point is. Now recall back at the other part of the video, T gives us all the points. So we plug in a value for T, it gives us another point on the plane, okay, or on the line. So we want to find the one that satisfies the plane. So we plug in each of these, the x, y, z, in for here, and that's the T value that's going to satisfy the plane. Okay, so let's write out what the equation of the plane is. X minus y plus 2 equals 9. And in for x, I'm going to plug in what x equals parametrically in the line. 2 plus t plus 2 times z, which is 5t, equals 9. And then solving this equation is going to give us the t value that will give us the point that is on the plane. So now this is the algebra. We have 3 minus t minus 2. Try to do my algebra right. Minus 2 plus 10t equals 9. And now we have negative t is negative 2t plus 10t is 8t. And then we have 3 minus 2, which is plus 1 equals 9. So we have 8t equals 8, and t equals 1. Nice, neat number, okay? So the scalar, or the parameter of 1 is the t value that will give you the point that's on the line. And then we just plug that in. X equals 3 minus 1. Y equals 2 plus 1. And then z equals, what's z? 60, so you have 5 times 1. So the point where they intersect, 3 minus 2, 1 is 2, 2 plus 2 is 3, and 5 times 1 is 5. That's where the lane and the line